All right, everyone, welcome. So far in your circuits class, you've gotten really good at building circuits, right? You know how to follow a schematic. But today, we're going to flip the script. Think of it this way. We're trading our builder's hard hat for a doctor's lab coat. Our job isn't to create circuits anymore. It's to heal them when they get sick. So, grab your multimeter, that's our stethoscope, and let's become circuit doctors. So here's our game plan. First, we'll get into the right headspace, moving from builder to healer. Then, we'll look at the main illnesses a circuit can have. After that, it's all about reading the clues, their voltage signatures. We'll lay out a step-by-step diagnostic plan, walk through a couple of real-world examples, and finally, I'll give you my golden rules for troubleshooting. Let's get started. First up, we're making a critical mental shift. This is all about moving from the mindset of a builder who just follows a blueprint to that of a healer who has to figure out the problem just from the symptoms. You see, building a circuit from a perfect schematic, that's like baking a cake with a recipe. It's predictable, everything's laid out for you, but troubleshooting, oh, that's a whole different ballgame. That's detective work. And these skills are universal. It doesn't matter if you're working on a fighter jet's avionics or just trying to fix a busted taillight on your car. You need observation, logic, and a system to hunt down that one tiny thing that's gone wrong. Our goal today is to start building that clinical diagnostic mindset.
Okay, so if we're going to be circuit doctors, we have to know the diseases we're up against, right? The good news is, for the series circuits we're dealing with, pretty much every fault you'll ever encounter comes down to just one of two basic problems. Just two. So here they are, our two main culprits. On one side, you've got the open. The best way to think about this is like a washed-out bridge on a highway. Bam! The road is just gone. It's a total break in the path. Resistance skyrockets to infinity. And all the traffic, our current, just stops dead. Then on the other side, we have the short. This one's more like a sneaky, unpaved shortcut that suddenly appears. It's a super low resistance path that lets all the current bypass where it's supposed to go. Our entire job is learning how to tell these two apart. Let's dive a little deeper into the open circuit. What actually causes it? Well, it could be anything from a resistor that's just burned out, a blown fuse, or, a classic example, the tiny little filament inside a light bulb snapping in two. Heck, it can even be something as simple as a wire that's come loose. But here's the key. No matter the cause, the main symptom is always the same. The circuit goes completely dead. Your ammeter will read 0 amps because there's literally no complete path for the current to flow. And now for its sneaky cousin, the short circuit. You know, the causes for this one are usually things you got to be really careful about in the lab. A tiny, stray drop of solder that accidentally connects 2 points, or maybe an alligator clip where the little rubber boot has slipped off and the bare metal is touching something it shouldn't. And unlike an open, which stops current, a short does the opposite. It's like opening the floodgates. The circuit's total resistance plummets, the current shoots way up, and you almost always get that classic telltale sign. Things start getting hot. So, how do we actually tell which is which without just randomly guessing? Well, this is the cool part. It turns out that each of these faults leaves behind a very specific clue. Think of it like a forensic fingerprint. We call it a voltage signature, and we can read it with our multimeter. All right, this is where things get really clever. In an open circuit, what's the current? It's 0, right? Now think about Ohm's law, V equals I times R. If I is 0, what's the voltage drop across all the good components? 0. So you've got all this voltage from your power supply. Where did it all go? It has to go somewhere. Well, it all gets concentrated right across that single point of failure, the break itself. This is the crucial rule. If you measure the entire source voltage across just one component, congratulations, you've just found your open. Now, the signature of a short is the complete polar opposite. A short, by definition, is a path with practically 0 resistance. So let's go back to our old friend Ohm's law. V equals I times R. This time, R is basically 0. So what happens? Well, it doesn't matter how much current you're pushing through it. If you multiply by 0, the voltage drop is going to be 0. So the diagnostic rule here is just as simple. If you measure 0 volts across a component that should have a voltage drop, you've found your short. Okay, let's pull all that together into a quick cheat sheet. For an open, current is 0, and the voltage across the faulty component is equal to the source voltage. For a short, the current is way higher than it should be, and the voltage across the faulty part is 0. This little table, this is really the heart of all our diagnostic thinking. Look, knowing the symptoms is great, but a real pro, a real engineer, doesn't just start poking around and guessing. They have a plan. They have a system. And that's exactly what we're going to establish now, a formal, step-by-step protocol for troubleshooting. I like to call it the APM protocol. Easy to remember: analysis, planning, and measurement. First, you analyze the symptoms. Is the circuit dead? Is a light dim? Second, you plan your attack. Based on the symptoms, you form a hypothesis. And then, and only then, do you move to the third step, measurement, where you pick up your multimeter to prove or disprove your theory. I can't stress this enough. Good troubleshooting happens in your head before you ever touch the circuit. And what's the very first part of that analysis step? A good, thorough visual inspection. You gotta use your senses. Use your eyes. Are there any scorch marks? Are all the wires connected tightly? Heck, even use your nose. That sharp smell of a fried resistor is unmistakable. You'd be shocked, but I bet that a good 50% of all faults can be found just by looking and smelling. Okay, so you've done your visual, you've got a hypothesis, and now it's time to measure. But please, don't just start randomly poking around. Be strategic. The absolute smartest and fastest way to find a fault is a technique called the half-splitting method. It's basically divide and conquer. You find the electrical midpoint of your circuit and take one single measurement there. That reading will instantly tell you whether your problem is in the first half of the circuit or the second half. Just like that, you've eliminated half of your suspects. It's brilliant. Enough with the theory, right? Let's put this stuff into practice. We're going to apply our APM protocol and that half-splitting trick to solve a couple of real cases. Let's play detective. Case study number 1. The symptom: the circuit is completely dead. So our brain says, probably an open circuit. Okay, let's use the half-splitting method. We'll measure the voltage right in the middle, after resistor R2. We take our first measurement and the meter reads 0 volts. That's actually great news. It means the circuit is perfectly healthy up to that point. The problem has to be in the second half. So what's next? We measure across the very next component, R3, and bam! The meter reads 10 volts, the full source voltage. Diagnosis: R3 is open. Case closed. All right, case study number 2. This time, we look at our power supply and see the current is way too high. We suspect a short. We half-split again. Right after R2, we take our first measurement and we get 6.67 volts. Now hold on. In a healthy circuit, we'd expect 5 volts here. Why is it so high? Well, if the total resistance of the circuit is too low, the good resistors in the first half drop a larger share of the voltage. This high reading is actually a clue telling us the problem is not in the first half, it's in the second half. So we measure across R4, and we get 0.00 volts. Diagnosis: R4 is shorted. Perfect. Wow, we've covered a ton of ground here. So to wrap this all up, I want to boil everything down to a few key rules, the really important stuff you need to remember every time you walk into the lab. But first, a really quick but super important tech note. Please remember this. You are a resistor. Your body can conduct electricity. If your fingers are touching the metal tips of the probes, you're actually putting your own body's resistance in parallel with whatever you're measuring, and that will completely screw up your reading. The rule is simple and non-negotiable. Hold the plastic, not the metal. Okay, let's bring it all home. Here they are, my 5 golden rules. Number 1, visual first. Look and smell before you measure, always. Number 2, know your voltage signatures. An open gets all the voltage, a short gets none. Number 3, divide and conquer. Use the half-splitting method to work smart. Number 4, trust Kirchhoff's law. The numbers have to add up. And finally, number 5, safety first. Respect what electricity can do. A short circuit means high current, and high current can be dangerous. So, I'm going to leave you with a little challenge. Check out this voltage divider board. It's hooked up to a 12-volt supply. Now, let's say you take your multimeter, you measure pin 2, and you get 0 volts. But then you move your probe to pin 3, and suddenly you're reading the full 12 volts. So what does that tell you? Which specific component has failed? Use the rules we've discussed today to pinpoint the problem. Thanks for joining me in the lab.